Hello. I wanted to make this video because I'm not entirely sure if Dr. Bekvar is going to cover Module 12 on his fourth and final. So what I'm going to do is I'm just going to go over the exam 4 review. This is review sheet B. And I'm just going to go over the Module 12 section. So the first problem, it says the solubility product for calcium hydroxide is 8 times 10 to the negative 6. Perform the calculation to determine the molar solubility of calcium hydroxide. Write the balanced chemical reaction for the process first. Okay, so we want to write a reaction. Calcium hydroxide, if you remember your solubility rules or if you memorized them for this exam, you know that this is insoluble. Hydroxides are insoluble except for barium and strontium. And that's because as you go down group 2, elements start behaving like group 1, right? And that's due to several factors that you're probably going to encounter in future classes, right? So calcium hydroxide is insoluble. However, everything is slightly soluble, even if it's not going to solubilize the entire way. So this is the chemical species. We know it's insoluble, but like I said, everything is soluble up to a certain point. So what this is going to do is it's going to reach equilibrium. And well, it's just going to break apart into its ions. We're going to get calcium ions plus hydroxide ions. And what we have to do is balance the reaction. Here we have 2 hydroxides, so we're just going to write 2 hydroxides over here. So this is the setup for the problem. Now it asks for the solubility, the molar solubility. These problems are similar to equilibrium problems. We're going to assign a variable to calcium and hydroxide. This is going to be our molar solubility. We don't know by how much, we don't know the molar solubility, right? But we know that it's going to be some variable S. We're going to name that variable S. And then hydroxides are going to be the same thing, right? But again, we take into account the coefficient. Okay, so this is our setup. We're also told we have a solubility product. This solubility product is going to tell us how soluble the compound is. We see that it's to the negative 6. So since the KSP is low, maybe I should say that. The solubility product is KSP. Since the KSP is low, right, it's times 10 to the negative 6. This is not soluble. Not that soluble, actually. So the solubility product, right, KSP, we can set up the KSP expression to be the concentration of calcium ions times the concentration of OH ions, right? And we have to take into account that we have this coefficient over here. Okay, so what this coefficient is going to do is it's going to multiply here 2 times the concentration of OH, which we already said is S. And it's also going to be an exponent. So the coefficient is going to do those 2 things. It's going to act as, it's going to multiply the molar solubility of hydroxide, and it's going to become the exponent. That's what the coefficients do. Now, if we had a 3, right, we multiply this times 3, and then it's going to be cubed. These concentrations are what we're trying to find out. These are concentrations of ions. If we had a question, I think it's the next question. Well, we'll get there, right? But these are the concentrations of ions, right? We don't know, so we assigned S to them. So what we can do is, using the KSP, solve for S. So then this becomes 8 times 10 to the negative 6 is equal to S. This is the S for calcium. And then times 2s squared. Yes. Now this 2, this exponent is distributing to this whole thing, is distributing to the 2s. It's outside. So we have to distribute this square. Okay, so we have 4s squared, right? If we simplify, if we expand this, actually. And now I'm going to take this s and multiply it by this, right? Because we're doing this, we're basically doing this. So this times s becomes 4s cubed. Okay. So now we know that KSP, which is 8 times 10 to the negative 6, is equal to 4s cubed. So all we have to do is solve for this variable s. And this variable s is going to be the molar solubility for calcium hydroxide. So first, we're going to divide by 4, right, to cancel out the 4. So then it's going to be 4 times 10 to the 8 times 10 to the negative 6 divided by 4 is equal to s cubed. Okay? Now, in order to get rid of this cube, we have to do the cubed root, right? And we do that on both sides. Now, my calculator is not that fancy, right? It's a pocket calculator. I think I got it for like $11 or $12. I don't know. Inflation is crazy. But this, actually, it does have a function, right? It has this cubed root function. But if your calculator is not that advanced, what you could do, right, is take this. Well, okay, let me first do this. So then this becomes 2 times 10 to the negative 6. If your calculator is not as advanced as mine, where it does have this function of the cubed root, what you could do, right, is take this, take the inside, and then put it to the 1/3 exponent, because this means the same thing as the cubed root, 1/3. Yes. So then this becomes, so then s is equal to this value here. Okay, let's move on to this next problem. So number 2 says, calculate the silver ion concentration in a saturated solution of silver 1 sulfate. So we start off by writing the chemical species. So this silver 1 is telling us that silver has a charge of +1, and we know that sulfate has a -2 or 2- charge. So we're gonna do this, right? So it's a silver 2 sulfate, and silver 2 sulfate is insoluble, so it's going to reach equilibrium, and it'll split off into silver +1 ions and sulfate ions, and then we'll balance here. Right, that's all we have to do. Okay, cool. So again, like the last problem, we'll set up a molar solubility. So that's going to be S, and that's going to be S, right? And we have a coefficient, so this is 2S. Once we put it in the KSP expression, then it'll become 2S squared. So remember, KSP is equal to silver ion times sulfate ion. We're given a KSP value, which is 1.4 times 10 to the -5. And then this is equal to, well, silver is going to be 2S squared, and then this is sulfate. Okay, cool. So again, like the last problem, we're going to get 4S cubed, and then it's 1.4 times 10 to the -5. So then let me just, so what we have to do now is solve for S, right? Because because yes, it's asking us for the silver ion concentration, and we know that the silver ion concentration is this value, right? And in our KSP expression, it's 2s, right? This 2s, not the exponent, but the 2s itself is the silver ion concentration. So if we solve for s, the entirety of s, we can plug it into here, and then we know how much silver ion we have. Okay, so then I'm going to plug it in. It's 1.4 times 10 to the negative 5 divided by 4, right? So we get this, and then we have to do the cubed root, right? So we get this value, and then, so this is our s. We solved for s already. S is equal to 0.015, right? But we want the silver ion concentration, and we know that the silver ion concentration is 2s. But the silver ion concentration would be this value times 2, which is 0.030, which is D. Okay, let's do number 3. It says the solubility of strontium carbonate is 0.0011 grams per 100 mil. 20 degrees Celsius, calculate the KSP value for this compound. We want to calculate the KSP value. So remember, first let's write our chemical reaction. So we have strontium carbonate. This is insoluble. So it'll reach equilibrium. We'll make strontium ions and carbonate ions, right? This becomes S. So then our KSP expression will become S times S, right? As to say our KSP will be equal to S squared. So, but we are told what S is, right? It says the solubility of strontium carbonate, solubility, which is S, right, for the whole thing is this, 0.0011 grams per 100 mil. What we want to do is get that to units of molarity. Once we solve for molarity, then we can plug it back into S, square it, and then we get our KSP. The easiest conversion to do right now is take the 100 mils and turn that into liters. So we'll have that. And then we want to turn the grams into moles, right? Because molarity is moles over liters. So we'll take 0.011 grams per 1 mole. Well, times 1 mole, and then the molecular weight of strontium carbonate is 147.68. We'll get 7.5 times 10 to the negative 6, right? Okay, this is moles. Okay, so then we'll plug the moles in here. And now if we do this operation, we'll get molarity out of it. And this becomes 7.5 times 10 to the negative 5 molar, right? So we have this value. However, we have to put it back into this because the KSP is equal to S squared. So then KSP would be equal to 7.5 times 10 to the negative 5 squared. If we plug that into our calculator, we'll get 5.5 times 10 to the negative 9, which is C. Okay, so now the questions are going to get a little bit repetitive as we go on. For example, 4 is like the first one we did, right? So I'll kind of go through it a lot quicker. Again, we want to set up our reaction, right? Magnesium hydroxide is insoluble. Okay. Then we have S and 2S. Now, we want the molar solubility for this whole thing, so we'll just solve for S, again, using a KSP expression. So again, KSP is going to be equal to magnesium 2 plus concentration times OH minus concentration. We're given a KSP of 1.2 times 10 to the negative 11. And then this becomes 4S cubed again. We do 1.2 times 10 to the negative 11 divided by 4. And then we take the cubed root of that. So then this becomes, so S will be 1.44 times 10 to the negative 4. Right? Just because all we have to do is solve for S. Right? Molar solubility of this entire compound is S. 5 is a bit tricky. Calculate the H ion concentration at 8.8 times 10 to the negative 4 molar barium hydroxide solution. Now, the funny thing is that if you call back to module 9, you'll know that barium hydroxide is a strong base, right? Like I said in the beginning of the video, as you go down group 2, the elements start behaving more like group 1, and group 1 is always soluble. So we know that barium hydroxide is soluble. So it won't reach equilibrium. It'll just go all the way. We'll get barium ion plus OH minus ion. And again, we balance it. Now, we don't really need to do S and S because we know by how much, we know the concentrations of these, right? We know that strong bases dissociate 100%. So if barium hydroxide is 8.8 times 10 to the negative 4 molar, then this also becomes 8.8 times 10 to the negative 4 molar. And barium hydroxide as well. However, we do have 2 of them, so we'll multiply it by 2. 2 times 8.8 times 10 to the negative 4. And this becomes 1.76 times 10 to the negative 3 molar. So this is our concentration for OH. We want H ion concentration, and the relationship between H ion and OH ion is 1 times 10 to the negative 14 is equal to H plus times OH minus. So if we want H plus, then we'll just have to solve for H plus. So then this becomes 1 times 10 to the negative 14 divided by the OH concentration. Okay, there we go. So we should get H ion is equal to 5.7 times 10 to the negative 12, which would be answer choice D. So this question is similar to another one that we did. It says the molar solubility for magnesium hydroxide is 1.8 times 10 to the negative 4 moles per liter. What is the KSP for this compound? So, okay. We're told the molar solubility, which is S, and it's in moles per liter. So then KSP becomes S squared. 1.8 times 10 to the negative 4 squared, which should be D. I think you're missing a negative. Yep. Yes, pretty straightforward. Okay, I'm going to skip to number 9, just because it's different from the others. 7 and 8 are similar to problems that we already did. So we'll just do 9 and then call it a review. 9 says calculate the minimum concentration of magnesium ion that must be added to 0.10 molar sodium fluoride in order to initiate a precipitate of magnesium fluoride. And then we're given a KSP for magnesium fluoride. By our solubility rules, we know that sodium fluoride is soluble, right? Sodium is a group 1 and fluorine is a halogen, and in combination with this compound is going to be highly soluble. It's like sodium chloride, right? So then this is going to split up into sodium ions and fluoride ions. If we have a concentration of 0.10 molar, then sodium becomes 0.10 molar. And fluorine becomes 0.10 molar, just like strong acids and bases. Okay, now let's set up the magnesium fluoride reaction. This is insoluble, so then it's going to undergo this. Okay, and then we have S and 2S here. All right. Now we'll set up the KSP expression. We want to know the minimum concentration of magnesium ion, right? Notice how we know the concentration of fluorine, right? It's 0.10 molar. So then this is the minimum concentration we need. So we're going to replace this 0.10 by this 2S, and then this becomes 2S times 0.10 squared. Okay, so then what we'll do is then do this, and then we just solve for S, and that S is going to tell us the minimum concentration we need because this S represents the magnesium ion. So then this becomes 0.01 times S divided by 0.01 divided by 0.01. And then 6.9 times, times 10 to the negative 9. S is equal to 6.9 times 10 to the negative 7, which is E.